Hello, welcome to the Hub. Ibrar Ahmed will talk about indexes in Postgres, which is a very important topic, and he's okay with you asking questions during his talk, but if you want to wait for the end, please wait for me to give you the mic so that it will be easier for the video captation and also for the one doing this wonderful work of the subtitles. Let's begin.
Yeah, thank you. So, welcome everybody. So we have talk about the deep dive into PostgreSQL indexes. So my name is Ibrar Ahmed. So let's get started. So it's my introduction. So I have been in software since almost 23 years, and with PostgreSQL, it's 17 years now. So when I joined first Enterprise DB, then now I am as a principal engineer in Percona. So I have authored 2 books on PostgreSQL. And that's it. So it's just the introduction. So initially we will discuss about the heap and indexes. So we will discuss about the what is the heap, the word actually that using in database, specifically in PostgreSQL, then the indexes. Then we will discuss about the PostgreSQL indexes specifically, and then index useful queries. So we will discuss about some useful queries used for the PostgreSQL indexes. So then, for type of indexes, what PostgreSQL support for that. So we will discuss about each and every one. So let's have an example that we have a book. So whenever we want to read the book, what we will do, we will start from the page number 1 to page number X. We want to read that book. So that's called a sequential scan. So I call a book a heap. That's the concept. So whenever somebody asks you to search some word in the book, so what will you do? You will start reading book from page number 1 to page number at the end of the book. So get that word, so where that word is. That's also called a heap scan, a sequential scan in a heap. So if you go to the end of the book, you can find an index there where you have specific words and the page numbers. So that is index that. So in database, it's 100% similar concept. So you go to the index, you scan the index, and you can see where that word is, and then you have a pointer. Let's think about not the page number, the pointer in a database word. So you have a pointer, then you definitely go to that pointer, a page number, and in that book, you can read the actual words. So pointer can be a 1 or multiple, because some words can be in different pages. So you have a 2, 3, 4, 5 page numbers. That means you have a 4, 5 pointers that pointing to the book. So that's 100% same concept in a database. The book is a heap. At the index is an index. So whenever you want to read the book, you have to read it sequentially. You can read it randomly, but it doesn't make sense at that time. So you have to read that sequentially. So in index, you can go and search some specific things in a book. That's the basic concept. So just giving the introduction about that. So in PostgreSQL, we're thinking about the tables, it's heap. Just calling that is a heap. So rows, you can call it a rows and you can call it a tuples stored in a table. But every table in a PostgreSQL has its own physical file. So whenever you create a table in a PostgreSQL, it will create a physical file on a disk. It can be a 1 or a multiple. I'm not going in that detail that when the file is more than 1 GB, then it has multiple files of that. But just have a concept that you have a physical file attached to a table. And definitely that's file in a PG data directory. I'm not again talking about the table spaces to have somewhere else your file, but in a PG data directory, which is a specific folder, as cluster folder where the PostgreSQL data files resides actually. So if you see here, No, sorry. What happened? If you see, there is a root directory, there is the mother directory, that has data directory. That's a PG data directory. So here you have a folders directory. And then you have a database table files. So here you can see that you can get the name of the file attached to the table admin. You have a table admin, and you can see that which file is attached to that table. So you can see here, and you can also go to the bash, and you can see that in this is the database OID, and this is the name of the file. So you can just go and search there. The other thing that why I'm telling you that these files are stored, the data is stored in a sequential order. When you are getting the data from table, you are getting that data, you are reading the data in sequential. Like in the next slide, you can see that when you are selecting the whole table, you are doing the sequential scan. Like in a book, whenever you want to read a whole book, then it makes sense to start reading from page number 1 to page number X. So you are reading that, that's called a sequential scan, and that makes sense. But if somebody asks you to read some word from the book, where the word is, and you start reading the book from page number 1 to page number X to just finding the name, that's also sequential scan, but that doesn't make sense because it takes time. So here you can see that in a database, we are just selecting all names from the table admin. So that 100% makes sense that we are reading the whole table and getting the names from that table. We are doing the sequential scan. That 100% makes sense. But here you can see that I want where ID is equal to 1200. And again, I am getting a sequential scan. That doesn't make sense because I am reading the whole table and just comparing that where ID is 1200, I am just reading that. That doesn't make sense actually. So, because it takes time, and you also see that it will take time. But in next slide, here, some of the detailed concept of that. If we have, we are selecting a content of the table from the admin where date time is something like that. So we have some condition here. So we have these ID, name, and date. So James, Alex, John, Bob, so we have different names there. And the important thing is that I told you that in a book we have an index that like that we have the pointer. So even the table has, every row in the table has its position, which consists of two things. One thing is the page number. Even sometimes you call it a page, sometimes it is called a block. So it's a 8K in PostgreSQL by default configuration. So the page number and the offset in that page. The first one, where you can see that the first one is the page number or block number, then one is the offset of that, where this row resides. So everything here, if there is a picture that is the block number 0, and you can see that block number 1. So you can see that, forget about this information, this is internal PostgreSQL information, so I'm not discussing it here right now. But you can see that the block number 0 and the offset is 1. So you can go here and you can read this one. So Postgres is reading like this. So I'm just colored that so you can understand the information. So here you can see that you have a tuple 1, tuple 2, tuple 3, different tuples or rows, and the storage information is stored in a per row basis. So every row has its own CTID, which consists of the page number or a block number and the offset. So whenever you are reading the row, you just go to that block number and offset and read that information. So that's the internal structure of the page of the PostgreSQL. The storage in a file, I told you earlier that every table has its own file. The information stored in a file like this, like the 8K pages, blocks, and the offsets. So everything is stored like this. So why indexes? So I already explained that indexes are the entry point to that table. So what is the first entry point in the table? Yeah, you start reading from the first line of the book. That's the entry point, but just start one. But if you want some kind of specific information, then you need a specific entry into the book, a table. So that's index provide the entry point. Index does not provide the actual information. There is something that I will do, that's an index only scan. I'm not talking about. Specifically, the index provide the entry point and the actual information is stored in the table. Exception is there. We will discuss that later. So index used to locate the tuple in the table. Definitely. Index is stored separately. That's important. That the index information is stored in again the similar kind of a file. The storage criteria is different. The information, like if you create an index, it will create another file for you. So is that information is stored similar to the table? No. It depends what kind of index you are creating. PostgreSQL has different index methods. It's like a B tree, it's a hash, it's a bin, gist. So every index has its own storage criteria. So we are discuss that later. But here you have a specific file for the each and every index. So here you can see we are sequential scan and we have created an index here. Index on admin. The admin is the name of the table and an ID is the column. So here you can say that index scan using IDX. The index is being used here. So okay. So definitely see the timing. Last time it was quite high. Same information we have accessing here. All right. So it's just an example. So let's go to the. So we will discuss about the indexes, concurrent indexes, partial, expression, index methods, and some index maintenance queries. So I'm not taking much of your time here about that. So creating an index. So we already created an index like you can see create index, name of the index, on table name and the ID. So explain, analyze, you are just getting that index is being used or not. So I'm just checking here. So I'm just skimming that because really basic thing, because it's just for the reference to be present in the presentation. So similar, you can see that I have created an index there. So created an index and you can see that admin index, I'm accessing that because I have the index name admin index, IDX, sorry. So I am looking at the, I'm looking at the IDX that's provide me the file that connected to that index. Previously we were seeing that the file corresponding to that table, but this is the index file. So that means you have an table storage, then you have an index storage. Definitely index is smaller than the table. We will discuss that why. Because we are storing the IDs only. Table has hundreds of columns, but in the index has maybe 2 or 3 columns, so we are storing 2 or 3 columns, but in a different storage way, not in a sequential way. It's a B tree, then it's a B tree storage, then hash, something like that. So that's information, that's the same structure we already discussed, but have the index file in that too. That's really important. Sometimes it happens that whenever you are creating an index, so you are locking the table, right? When you are creating, like your table is like 10 GBs or 20 GB, you lock your table. Because while you're creating the index, you are locking table. That's locking cause the problem because you cannot insert, update, delete on that table. So Postgres has some kind of a solution that if you write concurrently, it will slow down the process of creating the index. It's a slow down because, but it's not locking. You can update, delete, and insert in that table. But the process of creating index is slow. So definitely you can see that here as a 12303 millisecond to now create a normal index. And here?
Is that true even if there was no activity underneath? So it's doing some extra locking, such that it's going to take longer no matter what?
No, actually if there is an activity, it will take more time.
It'll take
even more. If you are doing excessively deleting, updating the table, then it will take more and more time. Yeah, it's a two parse actually is going on. Two parse is going on. The copy, and internally they're doing some stuff. Because that's the problem. Because if it's saying that it's deleting, that is releasing a log, let it delete, then again do the process. So continuously doing the process. When it sees that everything's okay, then it will give you to you. So what the Dennis has the question that if you have a too many operation on that table and you have a concurrently, definitely take more time than that. So, but the important thing is not blocking your application. If you have an application and it's not blocking, that's the benefit. Because you want to give the more priority to the user other than creating an index. So even you can previously in 1.2 version, they were only you can create index concurrently. Now you can re-index concurrently. If you have index, create index, then you can create re-index your index. Like rebuild, you want to rebuild your index. You can rebuild your index. So you can do that concurrently. So that's the word concurrently. If you don't write it, it will block your table. That's it. Expression index. What is an expression index? Actually, there is a lot of text here, so discussing each and everything is not more time, but it's for reference. Suppose you have a query where you are always using some kind of a function or an expression in your query. Is it better to store the actual value or the expression evaluated value in the index? That's the important. Like if you have here you can see that like David, like here we are creating an index from lower name. So we have a query lower name like David. So what we are doing, we are accessing the data from name and that name is stored in the index. So we extract that information and then compare that information. The other way, we can write, we can create an index and have that function while creating the index. That means you are performing that lower task once when you are creating the index, not every time when you are querying. You apply the lower function and store that information into the index. And when you are comparing, you already have the lower value there. But it all depends what kind of queries you have. If you have upper here, so what is the storing the lower value there? But you have to analyze it, that what kind of query you have, what kind of expression you have in your queries specifically. If you got your expressions good, manageable expressions, then put that into the index, you can get a better result. Because you are doing that expression once while creating the index, not every time when you are accessing the table index. It's just roaming around, I'm not wasting too much time on that. Yep. It's not like that you have an expression like lower, upper. You can have any complex expression you want. It's not like that you have a lower, upper, something like that. You can have a date, like you can see that a date plus interval 2 days is now. So I'm creating an index on bar with the date plus interval 2 days. I'm storing like that. So when I'm comparing, I am storing this date plus interval 2 days into the index. And while we are querying, we can get that information from there. That's it. So it's not matter that you have a small expression, you can have a big expression, but that expression must be present in your queries while you are writing that queries.
If we use the query just with the date function, it won't work. It
Yeah.
will use the index.
Yeah, it won't use the index. Yeah, even if you use that index, even sometimes you have a lower or something like, not this example, lower or upper, it will use that, but it again convert that. So what is the benefit? Because you stored that information like that, and you're again converting back.
I thought it's the other way. In this kind of index, it will still use the index, but in text field or bycast.
No, in text field, like you stored the lower values. When you are accessing, you set the upper. So it will extract the information from the index, but again apply that upper on that. So 2 times, yeah. So it's wasting your, actually you're wasting your information actually. But you can use that. So the partial index. Sometimes it happens that you have a huge table. Like I told you, every table has its own file on a disk. So that means it takes storage, right? So when you're creating an index, it has its own file. It also taking a storage space. So if you have a table of 1 terabyte, if you want to create an index on that, maybe it's 10 GB or 20 GB index. So while you are creating an index, you are not using that information. Like you have an information of 20 years, and you 99.9% you are using the information only for this year. But you created an index for 20 years table. You're wasting the space. Why you have that? So that's called a partial index. You can create an index like here, the normal, we have an IDX full on bar on that information. And we look at that, we are always accessing the less than value, 1000. So its performance is almost the same. The problem is that this one, 240 KB, 214 MB. If you create a full, like, it's not a big table, but I have created a full index on a table, like normal index, we create an index on table. It takes 214 MB. But here you can see that, oh, just sorry. So ID create an index where, while creating an index, I put in a condition on that. That create an index from the table only where ID is less than this. So it will not create index on the whole table. It will create an index just for that information, using that information. So the size is very low. You see the size. Here we have created an index on the whole table. So what will happen when we use an ID is greater than something like that? The index won't use. So because we are not using that, 99.9% we are using that less than 1000 attempt.
Might ask for ID equals 999. Would it evaluate and know that's less than 1000?
Yeah, less than 1000. Yes.
It does do that.
Yes. So the index, actually the optimizer of it decides which index is used. So you will see that it's no. So if you go, it will not use, and the heap scan, a sequential scan will be used for the table. But it's matter that it's one time query maybe you have, but 99.9% ability, but you reduce the size significantly. So index method, Postgres provide a different type of indexes you can take. And each index is for different kind of a purpose, right? It's not for every index is not for everything, but sometimes they are. So like B-tree index, the default index in PostgreSQL is B-tree. So when you are writing create index IDX on admin not using B-tree, it will automatically using B-tree because the default one is B-tree. This is optional using B-tree, but in that case only. But if you are talking about the hash, then you have to provide using hash. All right. So what is B-tree? B-tree is data sector, so you would definitely be -3 actually. You can go to the Wikipedia and you can search that what is the B-tree and what it's look like. But it is used for the less than, equal to, greater than, equal to, and greater than, almost everything. But there are some exceptions, we will discuss that. So here you can see that I have created a B-tree index and using B-tree, it's used, okay? So just same information. So in a block, you can see the same information is stored. This is heap, right? We have already discussed that this is heap. And we have that kind of information we want to access, right? We want to have an ID is equal to 8. So what's the one way to do that? One way is go to the block number 0 and compare ID is equal to 8, no. ID is equal to 8, no. ID is equal to 8, no. ID is equal to 8, yes. So what, and ID is equal to 6? No. ID is equal to 1 is equal to 6? No. So that means we have compared every value in a heap with 8. It is equal to or not. That means 6. 1, 2, 3, 4, 5, 6. We have 6 comparison here. But this is heap, right? But you know that we have an B tree index on that. So in B tree index file, I told you that index has its own file. So in that file, we have storage information like this. All right. So 8 is less than 9. Yes. 8 is less than 9. Yes. 8 is equal to 8, 0, 1, 1. 1 block, sorry, 8 is equal to 8, here we are here, 1, 1. 1 means block number 1 and offset is equal to directly reach here. How many comparison? 1, 2 and then that's okay. Here we did the 6 comparison. Here we did that only 2 comparison and we reach on that particular value. So here you can have a different value, you go there, these are the same CTIDs. I told you before that every row has its own CTID, which consists of block number or page number and the offset. So we directly reach from after 2 comparison. Here we did that as 6 comparison. That's the benefit of B tree. So you know that actual information, where is the actual information? Here. Charlie. It's not stored here. The actual information is stored here in actual heap. It's just a pointer to that. Right? That's interesting. Sometimes it happens that you have the whole information into the index. So you not only have the pointer, you have the whole information in index. So why just go to the pointer and go to the actual? So if I ask you a question, do you have a word PostgreSQL in your book? You go to the index and you can see, yeah, there is a written in the index. It has. You don't go to the actual book or see that, oh, it has. If it is in index, then yes, we have. So that's index only scan. Unfortunately, I did that in PostgreSQL. That's my contribution in the PostgreSQL index only scan. I did that 2009 or 10. Oh, so, yeah, closer to us. Sorry about that. So here you can see that the important thing is that like this ID, name and date, and we are selecting from here. And you can see the index scan is used. That means we want the information which is not present fully in the index. So it will use the index only scan or extract the actual information from heap because it's not available in the index. But here you can see the ID, 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 and the index is on ID. That means this whole information is present already in the index. So why go to the heap? It would directly say yes, and the index only scan will be written here. And the speed will be good, really good, the performance will be really good because it's no 2 scan. It's only an index scan, that's it. No heap access is done. That's it. So if you want to learn about that, you can see that ID, where ID is equal to 8. We are just getting ID from admin if ID is equal to 8. Right? So it will go 8 and 8. It said yes. It won't go to their head Charlie. Previously we want to access the Charlie. That's why we are here. Here we want to confirm that 8 is there. So 8 is there. That's it. We said yes. That's index only scan. So the second method is hash scan. So, sorry, the hash scan. No, the hash scan. The hash scan, you can see that I have select ID name from admin where name is equal to this one. So when we are creating an hash index, it's if you have that, let me index only scan. No, let's see first this one. we have created a hash scan. Create IDX hash on bar using hash. That's important. Previously we have a using BT, now we have a using hash. So we have that information that index scan using hash is be used. But when we creating this index, it will create a hash of that name and store that information. It will not store like a B tree. It will create a hash and store that. And most importantly, it's just for the equality operator. If you use that greater than equal to, it won't use because yeah. So go back. So here is the. It will create. You can see that ID name. We're just setting that name Alex, John, Bob, William, Charlie, David, Benjamin. So it will apply some hash function on that, and that is the hash value, and that is the CD ID. That means it will not make a B tree. It will have a table like that which has the hash values created by this hash function and the city ID is the same city ID. So when we say that Alex John, it will say the Alex Johns has post 0000 hash. So it will directly set the 00. So something there, it doesn't matter. So same. So that means it will calculate the hash and store that hash value. And when you have equal to operator, it will compare the hash and give you the value. So hash is the random value, make sure. So it won't be greater than equal to. It can be less than greater than. So it's only used for only apply on the equality operator, not less than greater than. So brain index, that's another index, interesting index. So if you have values, you can see this serially or consistent, or you can see that they has the correlation with the physical storage of the disk. Like you are storing the information January 2022, February 2022, and you have a block range. You have a block range of information. So instead of storing each row information, you can store the block range information into the index. Important. Like you can say that page number 1 and page number 1 and page number X has that block range. So it's one information. You are not storing that this row has CTID, this row has CTID like hash and B tree. You are storing the information of range. But it's only important you have the ranges in your data. If you are a random data in your like names, it won't work. But you have a range like from January data, February data, March data, and you have this kind of ranges in your information. So that's good. Then you can use a brain index. So what is the page number, the minimum value of the column and the maximum. It's not storing the actual one by one rows information. It's storing the range information. So why is that? You can see that brain index is used. So I'm just a little bit quick. Sorry about that. You can read that. That's information. So important is that not that its speed. Its speed is good, really good, because it's searching in the range, not the every value. But more importantly, this one. You can see that I have created a index using B tree, hash, and brain. And see, it's in MB, and you can see that this one, and this one. The size of the index. You can see that 48 MB and 21 MB, it's now size of, index in KB is 48 KB, and here 48.128 KB. Because we're not storing each information in the index, we're storing the block range information in the index. If you have a not block range, it won't work actually.
Is this really useful for range partitions?
For the range partition, yes.
I have a time series data, like pricing data, time series.
Yeah, for time series, it's definitely really good. Definitely really good, because it's built for that. Time series, yeah, that's a good word actually. But it's not time series, even if you have broken time series, like from this to this, that ranges of time series, then it will also work. So, because it's storing the ranges only. So, GIN index, it's a generalized inverted index. So, you know that, so it's a bit complex that it's not for that column. If you have that column of JSON B type and you want to extract some information from that using the index, that if you use that this name, it will create an index on whole row. And it will start comparing the whole row. But if you want to this name in an Alex and you want to create an index on that, how you do that? So we have our platform for that. So here I have to create an index name Alex. Within that, you can say that here name one using Jin. Within the, I am searching the name, but name is equal to Alex. Within it's sorry about that. I have in previous one. I am not searching this name is equal to Alex. I am searching this name is equal to Alex within the column. And you, actually, it will create a whole name. Yes, you create that, but it will create with the name this one, the whole.
What if you're only querying on like something within that B tree, or sorry, JSON B column, like some key specifically?
Like phone number.
Like phone number, like phone number.
Yeah. Did you create a B tree index on just that key, or did you create a J index on the entire?
Aha.
That's the name index, right?
Yeah, I think that's the Jin index, not B tree actually. It is what? Yeah. Okay. Yeah, that's good. Yeah, maybe I missed that. I can also confirm that. No problem. Okay.
You're not showing the crate, you're showing the syntax.
Yeah. Individual tree, yeah. So here I use the Jin index. Here you can see that IDX Jin is used here. All right. So JIS index, JIS is actually a generalized search tree. So if you want to find a point within a, you can see the square. So what index you can be used here? So I have example here, sample points. I have a created sample points, and I have on a table, I have an index for that box, and inserted some values, and then JIS index I have created on that. All right. Now I have a query that I can see that the value of B is within the like sample points, and this is the box. So I want to search that this values are within that box or not. So that's a complex, because JIS is complex. It's a framework. So I have created that example. I'm not going on too much detail because I already have done some minutes left. I have to discuss something more. But this is the whole example. So where the index is used, right? So where and what? B tree used for the index of most of the queries. 90% will B tree will fulfill your requirement. Hash used for the equality operators. So Brin for the range sequentially line up database like time series, something like that. So it's good for that. Jin used for the document and arrays, and used for the JIS is for the full text search and other stuff like the finding the geographical information, something like that for that. That's important actually. Sometimes it happens you create an index, and later you create another index, and PostgreSQL provides the way you can create an index with different name on same thing. Like you create an index foo1, foo and a, and you create another index foo and a. Same name, same ID, but you created two indexes. So it's a waste of space actually. It's a waste of space. You have wasted a lot of space at creating. But it sometimes happens in production. You create an index, you forget that you have indicated, you created an index with different name. So I used here, this is important because you have an index on A using hash and using B tree. That sometimes it will use hash, sometimes it will use B tree. That's important. That's doesn't matter. Like for equality, it will use hash. For greater than less than, it will use this one. But this is not important. This is a waste of space. First two. No, they allow that. They allow that. Shouldn't is a separate question, but they allow that. Yeah, but they did actually.
So some databases don't
in PostgreSQL it allows. In PostgreSQL allow that. So it's important. So I wrote a query here, which will give you that duplicate index of it. Like here, the column a B-tree index on table foo. That you have a duplicate index on foo table name and the column name A, and the B-tree is the type of it. That's the customized query. And here I put the count static greater than 1. You can see that how many. So you can drop that one by one, because it doesn't make sense to have a multiple indexes on same table and same column, right? That's a duplicate. That's another interesting query that I wrote. That query that you have that sizes like the table name, the index name, the table size, the index size, and the total size. So it's good that you have in a practice, you have this kind of information. Sometimes it happens their index is greater than the table size. So you have to re-index, and you have to remove the bloat from the index. So it's separate maintenance activity. So,
So in Postgres, is it can we assume that smaller the index, the better it is?
just smaller, actually the smaller is good. The space is important, always important space. But the important is the speed, because a space is actually not too much costly, but actually the performance is important. So sometimes a bigger index is good for performance. Like if you have too many queries which is accessing 4 columns of your table, you have 10 columns and your query is accessing 4 columns, so that have an index on 4 columns. It's a big index, but it will give you the better performance.
Right. But if you just create a new index with the same field as what's there, that new index will be smaller and it will start using the new one.
Yeah, start using them.
And then you can throw away the old one later.
Yeah.
It's
That's so the next query is
old school way to do it.
yeah old. I will go directly. Oh no, this one, not this one. Sorry. So size of the indexes, you can always get the size. It's a good query to practice on that, to see what is happening. So sometimes it's really good. You want to see that how you have created your indexes. Like you have created an 1, 2, 3 using hash, so you can get the index query like this. But using B-tree, because the default is using B-tree, so you have not doing that, but it explicitly put that. So if sometime it's happened, you have created a many index, you should see the queries, you can dump that query somewhere, so you can recreate that, you can practice that. So it's just
But here it brought 3 rows back, but it needs 4 rows.
oh, sorry, I removed one.
Oh, he must have cheated somehow.
Yeah, I cheated.
You know, something-
Actually, I accidentally created a 4 here.
Outrageous.
4 here, so I said no, 3 is enough, 3 is enough, so I removed that, but it's still 4. So you can see that?
Outrageous.
Yeah, you can see that I was doing that, creating the 4. So I have to put it 3 here. So a unique index. So PostgreSQL provide a way to create an index uniqueness of your column. So here I created an index foo1, foo2, and using hash, and this one index idx foo unique. This unique is important, right? So it's a create a unique index on foo column A, right? You have created that, so it will provide the uniqueness. So here the query, which will give you the information that which index is unique and which is not. Sometimes it's happened you created a lot of index, some unique, some not unique. So you need to know which index is unique and which is not. So this is the query that it will give, this is not unique, not unique, not unique, and this is the unique index. All right? So it's just queries that usually DBS can use that to access their database. So there are some views and table exists that you can always use that, like a pgstat statement, to see what kind of queries you have, because you have to monitor that queries. Sometimes 10 developers are writing the queries. So you monitor your queries using pgstat monitor that this kind of expression we are using. So this kind of an expression index we can build that. So it's like stat user indexes and something like that. So you can use that, and that's it. I will a little quick, but
No, that's fine. You still have five minutes for questions.
yeah, okay.
So, sorry, wait for the mic.
Yeah, wait for the mic. Sir.
I have a question on the partitioned indexes. Yeah. So if you create an index, any of the index, Brin or Gist or anything on a partition table, are these indexes automatically partitioned? Like in Oracle?
It's separate. Actually, that's a good question. Actually, I already have a proposal in PostgreSQL, but it's not accepted there till now. So, yeah, global index. So global index. So my proposal is still 1 year. So that you have to create the index. When you create an index on the parent table, it will create a separate index for each partition, not a one whole index for that. You have to create. It will create an index for separately each one, each partition.
Thanks.
What it does now, or that's what you want?
No, that's what it's doing. I want to create a global index for the whole big one for all the partition. That's in Oracle is called a global index. Then you can partition that index again. You can create an index on a partition table and then partition that index to access that. But it's not, still I'm waiting that it will be get accepted.
I got a question about the indexes that you have. For an example, you did a create index on A, and then you did a create unique index on the same column. Does that enforce the uniqueness of the data at that point?
No, actually, if you have a unique, then
another slide. Go forward a slide or two, I think.
Why it's not going? Yeah.
Yeah. So you got to create index, unique index on foo A.
Yeah.
So I'm assuming that would enforce a check for uniqueness when you go to insert data.
Yeah, it will enforce the uniqueness.
Okay.
Yeah. That's will enforce the uniqueness of that.
But don't you enable it from the constraint for unique?
Yeah, you can add the constraint later on too. But while creating an index, you can provide the unique one. Yeah, both at once. Yeah, it create an index and add the constraint both at one time. You can do that manually, like create an index this and put a constraint of uniqueness on this one too.
Yeah, but if I'm creating table with unique constraint, that should automatically create a unique index.
Yeah, that's what we are saying. It does. So there's a two-way. This way or this way, because I am talking about the indexes, so I am talking about from this way. If I am talking about the constraints, and then I will do that right. So,
You have shown us the
mic.
file. You have shown us the file location of the table.
Yeah.
Can you show us the location of the index? When you do LS, do you see a name?
Yeah. Actually, I
for
show that.
index?
Actually, I show that.
Oh.
I showed that. Maybe quite. Yeah. Yeah, here. That's you can see that admin index. So this is the location of the index file. It's not a table. Previously, I showed you only the admin, not the admin index. The query will be the same. This information has been changed. Previously, it was only admin. So it will show you the location of the admin table. Now it will show you the location of admin index. So it's the same thing. Query same. That's the name. I changed that.
Okay. One more question. For partition table based on time, do you recommend to create the block range index instead of B-tree?
Yes, because a block range is for the time series. You can say that time series is one of the major content of that for that. So you can use that on that because it stores the ranges. So in a time series, it is the range. So that's good for that.
And it makes your sequential scan go much faster because it doesn't have to check every row. It just looks at the block and says, I
I don't need that. It's just throwing out the blocks.
Let your sequential scan do would be much less by just eliminating blocks that it doesn't have to look at.
But how would that work in partition table? Because each table, each day is a different table.
That's a good question. Then if you are querying the partition table, right? If you're doing the global, then you have on a global index, you require that. That's global index separate, total separate question here. Yeah.
One last question.
Sorry, quick question. Are there cover indexes in Postgres? Cover indices basically in addition to the main
Yeah.
one?
Yeah.
Okay.
Yep.
Thank you. You didn't have it here, right?
Yep.
Okay.
No, don't have that here.
Can I add one small thing? You
Yep.
talked about create index concurrently. If you're running Postgres between 14.0 or 14 and 14.3, please don't do that because that's a bug that will corrupt your indexes, which is something you don't want. It was fixed in Postgres 14.4, but you should already be running Postgres 14.5 because it's out since at least 3 weeks. So
That's a really good point, actually. Yeah, I missed that. Thanks a lot. Thanks a lot for pointing this out. Yeah.
but that's very important.
Yeah, that's very important. Yeah. Okay, thank you. Thank you, everybody. So,